kind of from a tech background? Do we have beginners? I do kind of want to tail this. Taylor. Okay, so Omar, you are a tech background guy. Okay, what can I ask what that means?
I'm mostly doing more of a front end um um, type work, but I think I have a weakness in lead coding and algorithms and things, so that's why I'm joining it.
Okay, very cool. I'm excited to do this. This is the first time I have touched binary heaps in a long time. So what I'm going to try and do, my goal with this series, because so two of us have tech, or three of us have some tech background, two of us don't have some tech background. I am trying to make this series. The goal of this series is to be accessible. Now, of course, in doing data structures and algorithms, there is, if you are a complete newbie, this will be challenging. But my goal is to really make it, as understandable as I can. So that's my goal. And so I'm not actually going to be touching not all of the higher, there, because you can go a lot further than we're going to go today. But my goal is for you to come away with an understanding of what a binary heap is and how it works. So with that said, let me get started. And I really love now, I know only Omar has been brave enough to interrupt me, but I appreciate and love it when people interrupt and share their thoughts, like even if it's just like obviously questions, but also just like thoughts. Like otherwise I'll end up talking the whole time, which I'm prepared to do if necessary. But it's not necessarily what I like to do. So if you guys have anything you want to say, like please jump in and let me know. So with that, I am gonna start with a binary tree. So what is the point of data structures and algorithms? The point of data structures and algorithms in computer science, there are essentially specific ways that your machine can store data, right? And so, for example, a very common example of something that we need to do is we just need to store sorted data. So that's usually called a sequence, or we need to store data that are unsorted. That's essentially a set. So you have a sequence, which is for sorted data, and you have a set, which is for unsorted data, essentially. So that's pretty common. So let's say a very common use case, you can imagine this happens all the time, is, let me write in here. So one thing I need to do, I have the data A, B, C. I know this is non-numeric. But I know this is non-numeric, but you can think of it the exact same way with numbers. So I have data. I have data A, B, C, D, E, F, G, H, and obviously that is sorted, right? That is sorted. But I could just as easily, have data. First of all, if I want to invert that, or I could have, CAB. If I have like students, if I was ranking students, or it could be anything really. If I'm ranking my favorite beers, right? And I have a list of beers. I have a score because I kind of record them in my own. I have a program where I'm like, this is Joe's beer categorizer program, where I'm like recording over 5 years all the beers I try and giving them a score of 1 to 50. And then at the end, I want to say what were my top 10 beers. Then I need to go through, search through that unsorted data, and return the top 10. Or another way to think about it, again, because sometimes we as a humans might auto sort, but there's plenty of cases where data are not sorted, right? So what are ways that we can effectively do this? What is the reason that this is then important in data structures and algorithms? Because a very naive way to sort this would be to start at C and then compare to A and say, is A smaller? If it is, move it to the front. Is B so one option would be, okay, compare C to A, then compare C to B, then compare C to E, then compare C to D, and move, if whichever one's shortest, move it up front. So I can move C to A, and then I can move the A up front. Move C to B, then I move the B in front of the C, and so on and so forth. And eventually, at the end of the day, that kind of algorithm is going to have what's called an n squared, like O of n squared. That's, but the point is, so that algorithm, that's not quite as intuitive here from the methodology I just showed, but that's not the fastest possible sorting algorithm. And what we want to do are design algorithms that quickly are able to sort information, for example. So we need kind of a combination of how we store data and how we manipulate data. So data structures, how we store data, and algorithms, how we manipulate data, in order to reduce the amount of operations, the amount of computations that our computers have to do, and so that you can, when you search on Google, it's unbelievably fast. You can essentially get information on the entire web in close to less than half a second, and so that's absolutely amazing. So that's kind of the intuition behind why data structures and algorithms is important. That's just kind of a high level, because that's not really what we're trying to do here right now. But let me pause here and see if there's any questions or comments, anything anybody wants to fill in. I'll take that as a no. Since 3 of the 5 of us are unable to speak in terms of microphone, I'm assuming this will be a relatively quiet group. So that's kind of the intuition even at a higher level. So then I wanted to talk about binary search trees, and because that is kind of the data structure that I'm going to be using as a comparison for the heap. And what a binary search tree is it's a way of structuring data that is not going to be entirely unfamiliar to us. If any of us, when we think about family trees, those are actually sorted in a very real way. They're not, a binary search tree is actually not unlike a family tree in that so I guess that each node has at most 2 parents. It is a little different actually. But basically in a binary search tree, there's core features of this, right? So let me actually even demo a data structure that you can use prior to a binary search tree. So that's a standard array. So what an array is essentially a table of data that has 1 row. So if I had 10 things, I could store it in this array. Okay, so I can have a data structure that's essentially blocks. I can reserve a space in memory. What we're doing here in your computer under the hood is you reserve a space in memory. Your computer has memory, and you reserve a space in it. And basically, spaces in memory are literally little tiny blocks. They're literally little tiny, cells of memory. And so we just say reserve this contiguous space in memory. And now we can put an array there. So for example, we can put in our C is stored as the first element, A is the second element, B is the third, E, D, F, H, G, and so on and so forth. So that's one option. Another option, essentially, is we can have, in a binary search tree, you can have, and again, if this is your intro to data structures and algorithms, this is kind of a jump, but that's okay. And hopefully, I don't think you'll come away understanding all of the details, but it's kind of like if you're learning a foreign language, hopefully this will still help you with the thinking and how to structure. So if you're completely new to this, stick with me to the best you can. Ask any questions you might have. I know I'm kind of this is not really a data structure that is for intro level. I can share actually the YouTube links for earlier sessions I've done in this series that are for more total beginner level data structures. But this, this I think will still help you with intuition. And then, if you want to come back to it, of course, you certainly have the option, as I mentioned, I can share a link. So a binary search tree gives us the ability to essentially organize data in a way that each node in the tree has 2 children, at most 2 children. It could also have 1 child or no children. The leaves, for example, in this instance, have no children. So this is a binary search tree, and there's a couple of advantages to this, which we won't really be going over here, but again, this is important for us to kind of see, because this is a necessary data structure to kind of, it's not necessary to understand this, but when you start weighing the trade-offs, the pluses and minuses of using different data structures to store data, then this is a very helpful reference point, and it gives you a part of the intuition as to how the heap data structure is also going to work, because the heap is also a tree-like data structure. Okay, so a binary search tree, characteristics of a binary search tree. It has a single parent node, and each node has at most 2 children. So in this instance, in this particular tree that I just happened to draw, it can go infinitely deep, but each node has at most 2 children. So here we have a tree. This is a tree here. This is a subtree. This is another subtree. Actually, this is technically each node. This could be a subtree. Every node could represent the base node of a subtree. So this could also actually be its own subtree, right? It's kind of like saying like a subset of this is the full set. Obviously a subset also extends just to H, for example, but this is also one, like this is a subset, this is a subset, this is a subset, as well as this is a subset. So this could also be a subtree. Same concept. So another thing about binary trees, so this one, now this node has 2 children, and we could also have it so that this node has 2 children, or let's just make it so that this node has 1 child, for example. And of course, it is possible, I say of course, I guess that's not to assume, but it is definitely possible that you could have a tree that is imbalanced, right? You can have an imbalanced tree. This is called an incomplete binary tree, and we'll come back to that idea. But basically, you can already know intuitively what a complete binary tree is. Like this would be a complete binary tree. Like this, these top 7 nodes, because there aren't any kind of dangling, uneven depths. There's no uneven depths in the tree. This is obviously not a complete tree because it's extremely uneven, right? So that's kind of the intuition. One other note, and this is actually, I think, at a fundamental level, like how we have to think about how the data structure works under the hood, what makes something a binary search tree versus what makes something a heap. Let me pause here, see if anybody knows that. I'm just curious. No pressure either. Again, this is if this I'm not exactly sure where we are. We're all coming from different levels. This is, I'm kind of throwing some of us into the fire, but at this point, hopefully, it's about intuition, right? And intuition. So this concept of the binary search tree. Again, the array I think is relatively clear, where it's like a block-like data structure. The binary search tree is we have data that are kind of connected in a tree-like structure. What we have here is each node contains references to its child nodes. So in what a reference means in computer science, in computers, how information is stored in your machine, essentially at an operating system level or a C programming level, is you have memory, which can be absolutely contiguous. It can absolutely be contiguous. But basically what you get are linear addresses that increase. So they're not kind of random. It's literally like you have blocks of memory. You can think of it kind of as this array structure, right? This array structure you can think of as how your computer's memory is. It's just really, really long. It's really, really long. Your computer can have tons of information in it. And each of these variables tend to be, in a memory address, it's going to be very, very small. A very, very small amount of data is going to be stored in each memory address. So you have a very long block of contiguous blocks, or very long row of contiguous blocks. And so each of those memory blocks have what's called an address. And that's how your computer knows where to look to get a particular piece of information. Just like if I send you something, to your address, the computer will say, okay, I need to know this variable. This variable is stored at this address. I look up in my address book, the computer has its own lookup system. And so it looks there, and yeah. And so an array, what an array does is it takes an initial address and essentially blocks off thereafter in contiguous memory, and says all of this information is now stored in my array. Okay, so in the example here, let's say this first point is a memory address 3000. That's just arbitrary, but this is at memory address 3000. So B is an address 3002. And G is an address 3001, 3002, 3000, 1, 2, 3, 4, 5, 6, 7. So G would be stored in memory address 3007. So to make an array, what we do is we block off that chunk of memory. We say between memory addresses 3000 through 3009 are reserved. No other program can use this memory. And now we can write to that memory. There's no risk of other programs using it. And to access the 9th element, I just say, okay, my base address is 3000, and I add 9 to that because I'm looking for the 9th thing in my array. So that's kind of how that works. In a binary search tree, what we have is this piece of information doesn't necessarily correspond to a single block in our computer memory, although that's not infrequent that it might, but that's okay. We can, that's neither here nor there. How this actually works is we store an object. We don't have to define that term, I think, at a high level. So basically what we store is the following. We store the information that we want to store ourselves. So let's put in, let me actually put this in sorted order. So this would actually be CAB, E, this would actually be D, E, D, F, H, G. Okay, so I'm going to just get rid of these other things here. Okay, and so this information, essentially, this data structure stores more or less the same information. As you can see, literally the values are the exact same thing, and each node in this data structure, excuse me, each node in this data structure is going to contain 3 pieces of information. This is a binary search tree. What it's going to contain is it's going to contain the information that we want to store itself, as well as a reference to the node on the left and a reference to the node on the right. A reference, I'm like, oh my goodness, I have to explain so much stuff. I'm sorry that this is potentially somewhat confusing, so I do apologize for that. Again, I've been doing this series, and so I'm like throwing in terms that I'm like, yeah, if you've checked out the other ones, but I think everybody here today is new, so that's no problem. But I am sorry that there's so much background to this, but welcome to Data Structures and Algos. So a reference is essentially, you can think of it as an address. An address is actually for a physical location in memory. A reference will give you a pointer to an object, which can take up more than one address in memory. But what that means essentially is a reference tells your computer where to find this next object. This next object, maybe it's a full array, like maybe it's larger. We said it has a value and it has a reference to the left and a reference to the right, but who knows how big that value is, right? So in this case, it's a single letter. But if it was Shakespeare, Omar's coming from Shakespeare. If it was a Shakespeare quote, that would be much larger and would need appropriately more memory. And so a reference is actually just kind of like we literally also call it a pointer because it points to where you need to go go next. So each of these in the binary search tree contains the value that you need and a reference to the left and a reference to the right, to the node on the left and the node on the right. Okay, let me pause here. That's about all I want to say about binary search trees at this point. If I need to say more, I will come back to them, but that seems sufficient. Oh no, there's one other point I'll make, but let me pause here and see if there's anything else. No problem, welcome. One thing about binary search trees is you will see here that they have a specific order. So if we actually read this left to right, this search tree, like it's kind of weird that this E is at the top and then you have AF and then CB, D, blah, blah, blah. But if I actually read this left to right, and I'm gonna space this out a little bit more so it becomes a little more obvious. Let me scoot the A over here. If I mapped the array below this actually maps 1 to 1, right? So C is first, then A is next, then B is third, then E is fourth, then D is fifth, F is sixth, H, and then G. So that's why I chose that order. You can visit my information on binary search trees. I'm not trying to prove a ton there, but that is actually important. How the information are stored in the binary search tree are important, such that we can quickly get information from, like, this is essentially a sorted. This is a sorted. This is a sequence. This is information in which the sequence of information is important. So this data structure, it doesn't appear, because it's a tree, it appears, and it's also possible to think of it as kind of hierarchical, but another option is to think of it in a non-hierarchical way, that this works just like an array, but it also gives us certain properties that are advantageous when we're trying to identify elements quickly, of like, we want to find the largest element in this tree. Like in an array, actually that's pretty easy. We can jump in here. But if I wanted to know like have where F is, I can start at the top and let me do D. If I'm searching this array for D, if I'm searching an array for D, what I'm gonna do is I'm gonna maybe start at the middle, choose the midpoint of the array, something like that. That's an option. That's arbitrary. I could start here. I could start at A. I could start at B. It doesn't really matter where I begin. But on average, most of us would choose the middle because we can assume there's a 50% chance to the left and 50% chance to the right. And I'm looking for F, or excuse me, let's say I'm looking for, okay, so this one, yeah, this is right. Let's say I'm looking for F. So I start at E, it's the midpoint of my array, and then I say, oh no, this E is not equal to F. Actually, E is smaller than F. And so then I look to the right of my array. I only look in the right half of my array. And then I might jump to H and say, like, I chose the midpoint again there, and say, do I go right or left? And I go left now. And so now I look at these two. And then if I either land at F or I land at D, and then go right. Same idea here. If I am looking for F in this data structure, when I look at E, when I start at E, I know that F is larger than E. So instantly, I only have to look at the right subtree. I don't have to look at the left subtree. So that's, and then, same thing here. Then I would probably, but that's the intuition for it. So that's the intuition for it. So it is possible, obviously, for this to be hierarchical. When we think of like family trees that are organized in this way, we think of those hierarchical, but it is also possible to think of these left and right. And the advantage is, I know if I'm looking at sorted data, that if I'm looking for anything larger, everything to the left of E is smaller than E. Everything to the right, so this is actually a mistake here. How I have this done, obviously, because this D is smaller than, but you get my point. So I'm sorry about that. ABC. Oh no, CA. Oh, because this is in non-alphabetical order. But I think you still get my point. I hope you do. I think you do. Where, assuming that this is the correct order now, everything here is smarter. Thank you. I appreciate that. Everything here is larger, and so I only look in the right subtree. Okay. So let me pause here one more time. That's pretty much everything I wanted to say about binary trees. That's just to give us an intuition as to what binary trees are, how they work. I did a whole session on binary trees. I know that was super fast. So if you are not a binary tree expert, then that was a lot. But it's hopefully enough to give you an intuition to start looking at heaps. So let me pause here and see if there's any questions, and then I'm going to glance at my notes as well. Aren't there other ways to sort trees into arrays? Of course. Of course. Of course. There's there's all sorts of ways you could do it. Of course, you have the option to start, for example, top down as well. Like you could have A, B, C, D, E, F, and actually, we may do that. We may do that exact example. Yes, there are absolutely other ways to sort trees into arrays. Of course. But that's a pretty common. The scenario I just used is pretty common. Yeah, but again, not quite the purpose of for our purposes for today. The most important thing. So now we're going to transition over to a heap. Okay, and I'm going to do a better job with these letters, such that letters A. I'm going to do it like this. A, B, C, D, E, F, G, H. Okay, does anybody know anything about heaps? Because there is kind of like one thing that is probably the defining characteristic of a heap. I'm just curious if anybody happens to know it. If you don't, no worries. I'm just curious if anybody does. The thing about heaps, I'm talking about a data structure right now. I see. I know what you're referring to, but so a heap is, you can think of it essentially as a binary tree. So again, what is the defining characteristic of the binary tree? It's that each node has at most 2 children. However, the first characteristic is that it has to be complete, and the second characteristic is, if we don't remember complete, we did talk about that. I'll just leave that for now. It has to be complete. That's the first characteristic. And the second characteristic is that every parent node has to be less than or equal to its children. It's like each of its children individually. I'll say that again. So the first characteristic is that it has to be complete. And the second characteristic is, I hear somebody. And the second characteristic is that every parent, the value of every parent, essentially has to be less than or equal to, I meant greater than or equal to. I want to do a max heap. I'm doing a max heap, not a min heap. So a max heap, every parent has to be, and then we'll change out of letters into numbers here. Every parent has to be greater than or equal to its children. So, my question for you, is this a heap? Is this a heap? Omar, what do you think? We hear you.
What was the question?
So is this a heap? So let me start with the first half. Is this a complete? Is this a complete tree?
I think so, yes.
Actually, I believe you're right. There's one other thing I need to throw out there. I don't know if this is technically in the definition of complete or if this is actually a gap in my knowledge. That's also possible. I was going to say no, but I actually think it is complete. I take that back. I would usually see it like this. That's what I think of as complete for a binary, for a heap. That we kind of always fill to the left. But I think according to the definition that I gave, and I believe that, so I'm not exactly sure, but I would actually move this. I would have moved this from here to here. Now it is complete. So why is this complete, Omar?
I think it's complete because there's no, I don't know, I'm just guessing here.
Okay.
It's not an education. I think because it's not broken, or like each.
I see.
No, or. I
see what you're saying. So it's not like this. So that's a good thought. I believe I gave the definition earlier, but if I didn't, I also may not have given a full definition. So what complete means is that each layer essentially is filled out nicely before we add any other layer. So what I mean by that is this would be an incomplete tree. Okay, and the reason this would be an incomplete tree is that we have a fourth layer without the third layer being completely filled out, because this, you could fill out the third layer like this, or in other words, you could move this up here. Now it has two, now each node has two children. So essentially another way to think of it, I believe, no, that's, yeah, I'm not going to impromptu this right now, because I'll probably say something wrong. But so this first layer, obviously your base node always has exactly one node. Your second layer has exactly two nodes if you have a second layer. Your third node has exactly four nodes, and so on and so forth. Your fifth layer would have exactly how many nodes? Does anybody want to tell me how many it would have before we could have a sixth layer? Or a fifth layer, rather? So how many nodes would be in this for this to be complete and us to add another layer? How many layer, if this is the first, second, third, how many nodes would be in the fourth layer before we enter a fifth layer in order for this tree to be complete?
7.
7 more, exactly. So we'd have to add 7 more, exactly, because in total we would have 8. Exactly right. So we add, so the first, now can anybody tell me what is the kind of mathematical property or equation that defines the number of nodes in a row?
The parent must have a max of 2 children.
Okay, absolutely. So all nodes must have a max of 2 children. I agree with that. But I totally agree with that. What I'm asking is, so this in the first row, we have 1 node. In the second row, we have 2 nodes. In the third row, we have 4 nodes. In the fifth row, I know it's not written out here, but if we were to continue, if we were going to keep out a complete tree, we'd have 8 nodes, right? Because each of these would have 2 children. So each of these 4 would have 2 children. In our fifth row, we would have 16, because each of the 8 in row 4 would have 2 children. So we'd have 16 on row 5. So what is the definition? Like what is the number of nodes in a row? So the answer would be 2 to the row number minus 1, right? So in the first row, the first row, 1 minus 1 is 0, 2 to the 0 is 1, any number to the 0 is 1. In 2 to the first is 2, 2 to the second is 4, 2 to the third is 8, 2 to the fourth is 16, and so on and so forth. So that's essentially how we know how many we would have in a given row. Now, if we wanted to do, I'll leave that for now, actually. So let me leave that for now. So that sounds good. Any questions on what I just said? I agree with Omar. This is a complete tree. So, and again, notice the reason this is complete. The reason this is complete for our sakes, for us to be happy with it as a heap, is this is kind of like perfectly complete. I'm sure there's a special word for this that I can't think of right now, where you actually have like 1 in the first row, 2 in the second row, 4 in the third row, done. But this is complete because what we don't have is something like this, where this row is incomplete and we have the following row, if you see what I'm saying. So this would be complete. This would still be complete because this row essentially continues onward. You can have, and this would continue to be, this is still a complete tree, blah, 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 because we have this row is full. We have at most 2 children per node, and we're only adding to the left row, and we're doing it left to right, which I don't know if that's officially part of the definition, but it is how we're going to be thinking about it. Okay, is that clear? Is there anything unclear about that? Because that actually is important for us to understand right now. And the next thing I want to share is, so I said, is it complete? Check. Is every child less than or equal to the parent node? I'm getting a thumbs up from Sophia. Anybody want to disagree with Sophia? That's a smart choice. I wouldn't disagree with Sophia either, because Sophia is 100% right. So every child is also is less than or equal to the parent node. So that means we have here a valid heap. That's what that means. So this is a valid heap. I'm going to throw out one thing really quick. The other thing I want to throw out here is we also even have the opportunity, if we want, like we have this written in this tree structure. But if it's easier for us, and we're not going to be doing this, but I'm just going to throw this out there, we potentially can get some performance benefits on the computer side by, instead of doing this in terms of like actually building a tree in the computer memory, we also have the option of storing it in an array, but knowing how to like get between elements of the array. And I'll show you what I mean in just 1 second, as soon as I write these in here. Look at that. It even worked out perfectly, unless I miscounted the threes. 3 threes. Nope, looks good. So we could say, when I say this is the first element, what are the numbers? So let's call this first element. So what this is, I'll actually label this. So this will say number of nodes in a row. And this is really the max number, I guess. That's what I guess what I'm trying to get at. Max num of nodes in a row is 2 times the row, or 2 to the power of the row number minus 1. The other question I want to ask is, if this is 1, if this is node 1, and this is node 2, and this is node 3, and this is and then 4, 5, 6, 7, 8, 9, 10, then so the children of node 1 are 2 and 3. The children of 2 are 4 and 5. So what is the relationship between node number and, which we could think of essentially as index number in our array here. We can think of it as index number in our array here, because you can see here node number 1 corresponds to 10, 4 corresponds to 4, 2 corresponds to 4, 3 corresponds to 9, and so on and so forth. Actually, sorry, I'm also mistaking this. I'm calling this 1. That is a mistake. This should be 0. Let me double check what I'm saying here. Should that be 0 or 1? Should be 0. Exactly. And so then this is... Okay, so we start at node 0, because that now corresponds to indices in an array. If you're new to computer science, you're probably like, what did he just do? He just made the 0th element of the array. Or he just made the 0, made node the 0th node, not the first node. So how you have to think of it is how Europeans count their floors in their buildings. So in the US, when you enter a building, you enter on the first floor. When you pick up, if a phone rings once, you answer on the first ring. If same idea, but and so logically, we say if you enter a building, you enter on the first floor. It's not what the Europeans do. That is the ground floor, the 0th floor, and then you go upstairs to the first floor, right? So if you take the elevator and you press 1 in Europe, then you're going to end up 1 above the entrance. You're not going to end up on the entrance floor. So that's how you have to think of counting in computer science as well. We use 0 indexing. So 0 corresponds to the ground floor, which is what they call the first floor in Europe. And then they start essentially at the first floor, which is really, from an American perspective, the second floor. But anyway, so that's the idea. So in computer science, we index the way Europeans count floors and buildings, 0 indexing. There are mathematical advantages to that, which I'm going to not go into here, but that is something that you can remember. So we 0 index. So really, yeah, so now phrasing this differently, I'm actually even going to get rid of, it's really 2 to the r, right? Because the row number, if this is the 0th row, then if this is the 0th row, then we don't have to do that -1. And that's actually the reason why we zero index. There's so many mathematical operations that -1 would be necessary for. But we can worry about that another time. But that's just kind of what that 0 means. So what is the formula to get so my question is, what is the formula? I have an indices, like a node's index. What is the formula to get its 2 children? What is the formula for a node's left child? Like, what is the number relative to that node's number? Any guesses? So here we have 0, 1, and 2. That's not so helpful. More helpful is 1's children are 3 and 4. So, but its left child is 3. So so there's a lot of ways to get from 1 to 3, but we got the same operation here. So 3's child is 4, 5, 6, 7. So 3's left child is 7. 1's left child is 3. 3's left child is 7. So what might be the formula that allows us to compute the left child? What the answer is I'll just share it. And so the left node, like, how am I going to put this? I'm going to say the left child of node sub I guess. The left child of node, there we go. I love it. Who was that? Sophia, very nice. So let me make sure that looks right. Yes. You have written it in an unusual way, but I agree with what you wrote. So exactly. Blah, blah, blah. Let me make sure that's true there. Now that I'm saying this, I'm like, is that always true? It is always true. Yes, that is always true. Sorry, I'm just double checking here really quick in my head because I'm like, this is what I was going to teach you and I want to make sure it's right. It is right. Okay, so the left child of a node is, like Sophia said, 2 times the number of the node plus 1. Exactly right. 2 times the number of the node plus 1. So if this is node sub I, so this is node 0, then the left child, I don't know if this is perfect mathematical notation, but the left child's location essentially is node 2 to the I plus 1. So 1 times 2 is 2, plus 1 is 3, so that's the left child of 1. 3 times 2 is 6, plus 1 is 7. So that's the left child, and then the right child is just, I'm going to let Sophia answer, anybody answer. Very similar idea. Same idea, just there's the right child is always 1 more to the right than the left, so it's plus 2, exactly. Plus 1 in the previous, or 2 to the I plus 2, exactly right. So if this is 3, this one's always 4. If this one's 7, this one's always 8, so you just add 1. Exactly right. So that's how that works. That's how that comes together. And so the point of sharing that is while we are going to be looking at this in a data structure kind of way and thinking through it more visually. Let me see how we're doing on time. Ooh, I got about half hour and then I got to go. Okay, we're doing okay. While we're going to be looking at this visually, you have the option in a computer to store the information essentially in an array. You can store the information in an array and then just compute. Obviously these are then in kind of non-sequential order. The order of the data don't necessarily match. Like this is not sorted order, right? Necessarily, but the order of the data, I can always look at the left and the right child by just doing this computation right here. So I can search through the array's indexes because this is the 0th index of the array, this is the 1st index of the array, this is the 2nd index of the array, blah blah blah, and I can actually just use an array if I'd rather. That's a side note. If you're new to this, that probably isn't going to make any sense to you. But if you're not new, that's potentially a very valuable insight, right? So you don't actually have to build kind of out this tree data structure. You can just do this little math, which again, also one other quick point I'll make about this. Math like this is incredibly quick for a computer. We call this O1, which basically means it's a fixed number of operations. a fixed number of operations for a computer, even if it's like 100 operations, if you do like 100 computations, that's going to take if I'm not mistaken, I believe at a 1 gigahertz processor, which most of our processors are substantially faster than that. If I'm remembering the numbers correctly, takes about 1 nanosecond, which I may be mistaken, but I believe that's correct. 1 nanosecond to do a computation. So that essentially means it can do a billion mathematical computations every second. That's what a nanosecond means. One billionth. And I believe mine is like 2 gigahertz, which would mean essentially my computer can do 2 billion computations per second, per core in my processor as well, by the way. So that's kind of the intuition there. Okay. So this is very valuable for a lot of us computationally, but we'll set this aside now. This is kind of a side note, but we are going to leave this up here because you can think of it in terms of an array if you'd rather. Okay. So if we're using a heap as a data structure, to store data, just like an array, blah, 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 and we're storing essentially a sequence of data, what we're going to care about doing is being able to identify let's start, should I start with insert or delete? So let me explain the problem with insert before, and then we'll do insert here. So for example, in this data structure, let me actually go up to the actual array, like where we had our data stored here. So if we have data stored in this data structure, okay, so this is the data structure that we were looking at before. This is an array, okay, and as you'll remember, you'll hopefully recall, I explained how this is stored in your computer's memory is in contiguous chunks of memory. So if I want to insert something to be the third element, actually it's the second element in computer science talk, but so in front of this B, then what I need to do in my contiguous array is actually, how I would actually have to do this is I actually literally have to move the G over, then I have to move the H over, then I have to move the F over, then I have to move the D over, then I have to move the E over, then I have to move the B over, and now I've got a hole there that I can insert information into, and I can put in a P if I want. Okay, so that's the information. So that is called an O of N operation. What that means is it's linear time. It means that my computer is not able to do, that's only like 15, 10 operations that we just did. It's move this one over, 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 right? But the point there is that if I want to insert something at the beginning of my array, if I want to insert it at the end of my array, it's nice and easy. Oh, done. No additional operations needed. But if I want to insert at the beginning of my array, I have to scoot all of these over into the next hunk of memory. And so as your computer program gets very large, or as the data stored are large, then that can take a lot of time. Okay, a lot of time, again, a half a second delay is annoying. Like we all click away from a website because it didn't load in a half a second, right? So it is, time matters. So the concept here with the heap is that we are trying to store data and have a data structure where I can insert into the middle of my sorted data, or it doesn't have to be sorted, but my data which are stored as a sequence in which order matters. So it's not just like I don't care what information I get. I care that it's sorted. I care that, I care about the order of the information, which I think is very, very common, obviously. So when sorry, I lost my train of thought. So the point here is, how is this data structure potentially helpful relative to the array? The way in which it's potentially helpful, if I want to insert into the array, as we just showed here, if I want to insert into the beginning of the array, I have to scoot over all other pieces of information, right? I have to scoot them all over. So that's an n number of operations. That's the length of my array number of operations. In this example, in the heap, I don't have to do that. So let me start with a very simple example. Let me say I want to insert at the end. So where would I insert this? Like where do I have to insert this? I'm adding another piece of information. We're going to call it 0. Any guesses? Or any guesses? But you guys know this already. Where do I have to fit this into my data? You don't have to look up here anymore. I'm talking about into this tree structure. So it has to go onto this node. It has to have this 3 as a parent node. That keeps it complete. So we don't want to add it down here. We don't want that. We don't want to add it over here. We want it to go off this parent. We're building out each row left to right. Okay, so that's crucial. Now, let me actually change this from a 0 to a 2. Is that allowed? Is what I just did, does that violate our heap constraints that we talked about? Would I be allowed to do this? Have a 1 and then a 2 is the right node on a heap? Yes, very good, Sophia, very good. Exactly right. Yes, because the comparison that we talked about, very, very good, is that we care about how each node is relative to its parent. So 2 is still less than or equal to 3. 1 is still less than or equal to 3. But there is no comparison that we're making between the 1 and the 2. So it is absolutely allowed. Very good. So now we've added 2 to our heap. And so the insert operation at the end is very nice. Okay, that's very nice. Now, let's say we want this to be sorted. So I'm actually just going to go ahead and delete this up here because we don't need to worry about this anymore. Now let's say what I wanted to do is insert 20. Okay. That is essentially not allowed. So how do we solve that? I'm going to give you guys a second here. How do we solve that? Or like, I want to insert now 20. So I'm going to kind of need to put it here. So how do I solve that? This is where a data structure and an algorithm come together. So I solve this. I solve adding this 20. We're working on what we're going to call an insert operation here. So we've added the 20. It would have to go to the 0 index, but I don't know how. Very good, Sophia. Very, very good. Excellent job. That is exactly right. So Sophia correctly identified that this 20 is going to have to come to the 0 index. Why is it going to have to come to the 0 index? It's going to have to come to the 0 index because it's the largest number. And so it's, if the rules of the heap say that each number, each parent needs to be at least as large as its children, we're violating that constraint right here, right? So we add a 20 at the end of the heap because that's essentially where we have to add it next. And so how we solve that, we have the option. What we can do now is we access this node and we swap it with the 20. So now we have a 3 and a 20 here. Okay. So now we've sought the 3 and the 20. Okay, so now this subtree, this subtree, let me expand this over here. Scoot this over here. Sorry about this. So now this subtree, which we were looking at, this with the 1 and the 3, is a happy camper because it is now it now does no longer violate our rules of the heap. However, this one does still violate the rules of the heap, right? So this or newly violates the rules of the heap. That's the word I'm actually really looking to say. So we do the same process. We would take this 20 and we swap it with a 4. Oops. Take the 20 and swap it with a 4. Okay. And now this subtree is also once again compliant, right? This whole subtree is once again compliant. Now the point of this is, the advantage here is when we know that each node is at least or is no larger than its parent, and we swap a larger node for the parent, like the parent becomes larger. So let me put it back to where we were a second ago. We had 4, 4, and 20 here, okay? When we swap the 20 and the 4, we know that there is no chance that this will become upset, because the only thing that we're doing is making the parent larger. We're making the parent larger. So there's no chance that we're going to throw off the balance in the left tree, if you see what I'm saying. Like, this already works. We already knew this worked, right? We already knew that this worked. And now we're not throwing off any balance, because we're only making the parent larger, so there's no chance that we're suddenly going to violate the principle on the left side. There's no chance now on the left side the child will be larger than the parent. There's no chance, right? Because the parent was smaller previously. It used to be a 4 up here, not a 20. And now it's a 20. And that's the point. When we're swapping, we're actually always swapping so the parent becomes larger. Same thing here. So we have a 20, a 10, and a 9. This 20 is too large, and so we swap with the 10. There's no chance that 9, this balance with the 9 and the 20 gets disturbed, because the 10 is increasing. The parent is becoming larger. So there's no chance that the balance between the 9 and the 10, where the 9 has to be smaller than the 10, there's no chance that it's getting thrown off, because we're making the parent larger. We're swapping the larger one for the parent. So there's no chance we're violating any of the other subtrees. Okay? So that's kind of an important point as well. So where we kind of end up there is, now our insert method, we've now swapped all the way up, and our 20 is appropriately sorted in our data. Okay, our 20 essentially is now our largest node, and or our largest value, and it's at the top of the tree. Now, what is the advantage of doing this? If we're trying to sort data, we want to have these data sorted. The advantage of doing this in this data structure is, how many operations did this take? This took a swapping operation here, so we swapped once, then we swapped twice, and then we swapped it 3 times, right? So we insert here, we swap once, we swap twice, and then we swap a 3rd time. So that's 3 operations. If, on the other hand, we had that array structure coming all the way over here, and we had whatever it was before, 10, 9, 4, 4, 4, 3, 3, blah blah blah, and so on and so forth. As we saw, we will have to move to add the 20 to the front. We're gonna have to move each of these over. So we're gonna have to move each of these over. So we have 10 elements in this array, I believe. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so we have 11 elements. Oh, because the one we just added. So that would have been 10 operations, right? We had 10 or 11 operations, right? So we had 10 elements. We have to move each of them over. So it's 10 operations right there. Versus here, this way, it's what's called logarithmic. It's logarithmic because it's a log of the number of operations. So essentially, instead of having to do 10 operations, we only had to do 3. If our tree was a lot higher, then it would be, then obviously you'd have to do some more operations in that way, but it grows at a much, much, much slower rate than linearly. So linearly, like every time you add a new one, that's another one you have to scoot over if you add another element, versus this way, you only have to do the log of the number of elements you have. If you're not into the math, don't worry about it, but the principle, I think, is clear. In this way, we kept our data in sorted order, but only had to do 3 operations. And that was actually the worst case scenario. But in the situation where we have to move every single item over to add something new at the beginning, it's a lot more operations for the computer. Okay, so that's kind of the first thing. People are starting to drop off. I will take that as a sign as I should wrap this up. I got to go at 7:30 anyways. But Sophia, you are kind of my star student anyway, so that works out well. Let me add one more. Let me add just one more thing here. Let's just do an insert and a delete for this. So we've just done the insert. How do you think I would do a delete? I know you have to type it out. I'll give you a minute to think about it though. You don't have to type it out, but I will give you a minute to think about it. Like, this is how we just inserted. So I'd like you to kind of take a second and think about how would I delete here. I like what you wrote. It's a good thought. It's a very good thought. Yes, that sounds right. That sounds right. So, yes, that sounds right to me. Hold on, let me just take a glance at my notes here, see if there's anything else I really want to talk about really quick. This should work great. So basically, one of the things that's worth noting about this heap is that there's only one place we can delete from, right? So that the only place that we can delete from is right here. That's the only node we can delete, because if we delete any other node, if I delete this node, for example, we now break our assumption that we have a complete tree. And so we don't have the option to delete any other node other than that last node. Okay, and obviously if you delete this node, like, what's going on? You obviously can't do that, right? And so, but this is also a leaf. I know this is a leaf, but you still can't delete that because now we've broken our assumption of a complete tree. So we need whenever we say we want to delete something, we need to get it to this node so that we can then delete that node. Okay. So what this means concretely, we just did the 20. So let's not do the 20 again. Let's do the 10. Okay. So if we want to get the 10, in this case, okay, so let's actually even make this, just for where we are today. Yeah. That's fine, because obviously you can also have the complication. I'm just going to throw this out there. You can have the complication that this is a 5 and you're going to, now making this swap downwards can cause a problem. You can break that. If we swap the 10 and the 4, we'll have a problem. But we're not going to do that. We're not going to make that assumption for this purpose. So when we swap this, Sophia, I understand. So your question now was when we swap the 10 and the 4, which is what we're about to do, because our goal is to get the 10 here. Okay, our goal is to get the 10 here to this node. Necessarily, by putting the 10 at this node, we know we're breaking the assumptions of the tree, right? Like, it cannot last like this. Like, this is kind of what is the word I want to look for? Like a temporary measure, or what we're doing is we know that 10's deleted. That 10's getting deleted. We know that 10's getting deleted, but what we're trying to do is actually move it into the delete position, which will break rules along the way. However, but what we're doing is once that 10's in the delete position, we delete the 10. Now the rest of the tree isn't breaking any rules. That's the point. So the 10 is going to end up in this delete position, and obviously because the 10 is at this position, that is already breaking a rule, right? But the point of this delete exercise is not to worry about the rules getting broken along the way, as much as to make sure that when we finish and the 10's gone, now our tree is completely valid. If you see what I'm saying, because the point is the 10's gone anyways. So this is just a temporary step. So we're restructuring our tree such that, or our heap, such that it's valid as soon as the 10 is gone. Okay, that's the idea exactly. So the 10 is here. What we're going to do is the same operation in reverse order. So we're going to switch with the 10 and the 4. And so then we're safe. And then essentially what we switch with the one of the three. And I mean, and it is that simple, right? And then we delete this. Now, in this case, everything is happy and healthy. However, let me go back here and make it, flip the order of this 3 and this 1. Oops, and this was a 4. Because this is also a perfectly valid tree. Or a perfectly valid heap. That's the word I'm looking for. A perfectly valid heap. So I can switch the 10 and the 4. And now, what I need to do in this case, what do I need to do in this case? Bring down the 10. Right, but the point is, oh wait, did I, yeah. So if I bring down the 10 and I put it right here, then obviously I've got this case. So when I delete this 10, it doesn't work. Because now this, what doesn't work is this 1 is larger than this 3. So we're breaking that assumption. So there are ways that you can handle this. It has to go to the left child position. Exactly right. And what you could then do, that's exactly right. And then what you can, how I would think about this. So let me put this back how it was. You bubble to the max side. You bubble down to the max side. And then once you're here, what I would essentially do is flip. So I delete this, and that's, and essentially now this is showing as a right child, but then I just move it to a left child. If you see what I'm saying, like this one now just has one child, and so that works okay. That there's more you can do on that, obviously, but I think for today, our group size has shrunk, and so I think we're gonna leave it. I think we're gonna leave it at that. So, Sophia, thank you. Yeah, I appreciate it. Thank you very much for joining me. So, a couple things. You are very naturally good at this. I don't know if you are a technologist already, but if you are not, you should think about being one. A couple of things. So, my email is joe@passionclass.co. And if there's anything you need to know, feel free to email me. Let me think if there's anything else. And then, yeah, I am doing a series on data structures and algos.